Welcome to this fourth installment in the series on the Dirac equation. The purpose today is to present a classical field that represents the fermions of the standard model as we know them in our universe. And the code word here is classical field theory. I am not proposing any quantum field theory different from the one people are working with. It's not a many-particle theory, it's the classical field that I'm working on. We start with the legacy field presented in the last video that had only positive charge densities, so it's a presence density, and the flow, it's flowing in one direction, and the energy of antiparticles is negative, and the momentum is negative, so that the momentum points in the opposite direction of the velocity. We need a theory that doesn't do that. The theory on the particles work consistently and very nice. So the problem is what to do with this. And let's first consider Feynman's adage that antiparticles move backwards in time. That should mean that we need to change sign on those where time occurs, like the flow, but not the density, because it's mass or charge per volume. No time occurs here, whereas it does here. It's charge per square meter per time. On the other hand, this is a temporal component of a vector. So maybe that's what makes the difference. In any event, we should change signs on all of these four quantities for whatever reason. Whatever our reason for doing it. But if we change any sign here, we'll lose charge conservation, energy conservation, and conservation of momentum. And since the momentum goes into the adding energy, then we'll use energy conservation as well. So what do? We have to follow the procedure and define a field where these signs come out as the opposite of what they are. The next thing is antiparticles travel backwards in time. What is an antiparticle? So let's make a test. This guy, is that a particle or an antiparticle? Which kind of wave do you think it represents? We have just evaluated at the center and the time you have here. What you find in the books is that it's the sign of omega, which is negative. It's minus 0.8. So it should be an antiparticle. But we have seen that the sign may become positive if it has a great potential energy. Or when we are talking real physics here in our universe, then if the particle is bound to such a degree that omega becomes positive, giving a negative total energy. So it could be a bound particle. I propose we take the sign of the spinor here. You see C22, it's the complex numbers or the complex C4 with this scalar product. It's not an inner product because it may vanish. Actually, it vanishes on a hypersurface, which cuts the space into two different parts. A positive part and a negative part, wherever that is. I propose to use that distinction to determine what is an antiparticle and what is not. So, taking the scalar product of this guy with itself, it's 1.4, 1.7, 3.1, 1.6, 2.5, 4, minus 1.5. So it's negative particle. Therefore, I should think that this would be an antiparticle. We have to change sign on all of these guys when we are dealing with negative spinors. So one way is to do it is to define an alternating scalar product, the A here for alternating, and then multiply the scalar product by the sign of A with itself. Other ways are possible, and you can investigate them at your leisure. This is just what I've done. It felt better. Now we just follow the rules. We have defined our space, our scalar product, which is obviously Lorentz invariant, isn't it? And then we define our Lagrangian density. So we have the integral over space and some period in time gives the action. And then we get the Dirac equation and conserved quantities. It's obviously gauge invariance, so we get a conserved charge. It's translational invariant, so we get an invariant energy, whereas as usually omit the Lagrangian density here, and momentum. So we have this conservation of charge, conservation of energy, conservation of momentum. And they come out right here. What we should do to check whether it works is, of course, to submit it to Klein's paradox. So we take the same example we had in the last installment, Dirac 1, and actually we do have a change. The antiparticle here, we have a change in direction of the flow. Oops, as you can see, the flow is not continuous across the boundary. On this side it's in this direction, on this side in the opposite. Let's just check the other as well, with eta equals minus 0.8, and the same thing happens. On this side we have a total current this way, and on this way. So what happened was exactly what I told you would happen if we just change sign. And I just follow orders. I defined the scalar product, I wrote up the Lagrangian, and then everything falls together. I'm so sorry. But I know who's to blame. The mathematicians. All right, I couldn't help pulling this prank on you. Sorry about that, but I couldn't help myself. If you followed the installment from the first, or followed the series from the first installment, then you probably already know what we need to do. We need to derive the boundary condition. And to do that, we assume that we have a positive wave to the left of the xy plane and a negative wave to the right of the xy plane. And then we shall find the derivative of the action, and that should give some condition, some boundary condition. Obviously, we cannot assume that the wave is continuous across the boundary. So we open up for some discontinuity, some boundary condition, and that boundary condition should hold for both psi and the variation. So to find the directional derivative, we first compute this. And the only guy that's interesting, that's derivative with respect to z. So the point in front of here I've omitted for a reason, because it would be confusing. So index z to psi means derivative with respect to psi, and the same with phi. We need to, this is the only interesting part, which comes from this. And we split up the integration from minus infinity to naught and naught to infinity. And instead of psi, we must write this, which I have just put 3 dots for. And you know the drill by now. The directional derivative comes out like this. This gives, or rather, this one gives 2 terms, phi and psi and psi and phi, psi-phi. So that's from the first. This one yields this one, this, etc. Next, this is fine, it's just the scalar product with 5. Here we need to make partial integration, and here, and here, and here. So from minus infinity to infinity, we need to insert the value at naught from the negative side here, psi, gamma 3, phi, and all evaluated at naught, but from the negative side. This is what we get here. And the other ones as I've written them. So only 4 terms. And what do we do here? We isolate phi. So that means gamma 3 must be moved to the other side. That's easy because it's self-adjoint, no problem. And another thing I forgot telling you, I did, the alternating scalar product, to be able to move gamma 3, I change it to the ordinary product, and that's where the minus here comes from. So when z is positive, we need to change sign on the scalar product. So the minus here becomes plus. And also I put in the part that has psi in it, So here we must change sign, not here. Here we must change sign, not here. And to get on with it, I assume a boundary condition which is linear. It's a very general assumption. Actually, my first guess was that it would be diagonal. So, but let's try it with any A. And maybe we should also assume it's unitary. Then all the pluses we have over here, psi plus is substituted with A psi minus, psi plus with A phi minus. That's here. And then we move A, isolate phi minus again, and we move it over so it's A star, the adjoint of A. On the next frame I've just copied this. As you see, finding the boundary conditions is actually challenging. This is the last line from the last page. And now we collect the terms with phi minus. And here, so that gives two terms. And now we see that we do have a symmetric expression. And we can write up the derivative minus h bar minus h bar c halves, and then we have I on both the components. It shouldn't have been in here, which we take outside the parenthesis. So this is the derivative. And that's a condition on psi minus, which must be anything. So that means that this guy's gonna vanish. I worked a little more on it, but let's just assume now that it's diagonal. And insertion gives this guy, and many choices are possible. And that's because if we take this solution, A equals 1 and D minus 1, the simple solution, then on to the right of the boundary, any gauge may be chosen. So of course it must have a multitude or a family of solutions. I'll just show you that I did some work on the boundary condition. So we define the scalar product. I use G0 to do that. Oh, that doesn't work here. We need to go down to solving for boundary conditions. I define the gamma matrices and then an arbitrary matrix, and then I say let's assume that it is unitary. If it's unitary, then we may multiply it by A star cancel, so it's just means that A and gamma 3 anti-commute. And I'm sure some of you knows all the matrices, the entire family of matrices that commute with gamma z. But actually I thought, sorry, what about changing sign, crossing some other direction? So maybe it would be a good idea if this held for all spatial gamma vectors. So it also holds for gamma 1 and 2. That's what I tried. So let's see if we can find a unitary matrix A, which anticommutes with the spatial gamma matrices. That's this 3 guys. And we solve the equations, and it turns out that it's diagonal, or there are some guys here, or both. I thought, oh, this looks very interesting. This, if the diagonal vanishes and we have M42, then we would change spin, or rather there would be spin conservation in some way. That was my thought. As we'll see later, that's actually probably a misunderstanding. But I looked for a solution with 2 or with A here instead. And it's a little difficult to find one that is unitary. We can find one that is anti-unitary. That's very easy. But they don't seem to solve. You see, I defined F to be exactly the equation we had. Gamma 1 conjugate M gamma 1, that actually is a representation of the adjoint in our scalar, with our scalar product. And then we should multiply with gamma 1, and then the matrix itself, the sum should vanish. So I just wanted to do that. And if we put in a matrix here, let's just try it. Oh, actually, I didn't give it a name, didn't I? Up there, I think I named it. Yeah, X1 it's called. So we just say X1. Then, what? It can't really vanish very well, because this is the modulo of A, which is larger than or equal to naught. So this is larger than or equal to unity. So it doesn't work. Well, all in all, I end up with this solution as a possibility. That's our boundary condition. And solving that, I did go through the details of it. I defined the incoming wave, the reflected wave, with a coefficient of R, moving, and the transmitted wave. Of course, it's not necessarily transmitted. We'll see that in a while. And there's a coefficient Ts. And as you see, the charge density is negative. And if eta is positive, the current is to the left. That's the left for you. And that means the particle is moving to the right. So minus kappa z of course, if kappa is positive. And now we solve for the Klein paradox. And here we have to see the first coefficients agree and the third coefficient change sign. We get the solution, and I work out two examples which I shall show you now. The first example with positive eta and zeta, and it looks very much like the one you know, except there's some subtle changes. Now we do have charge conservation, and that means that this incoming wave will induce a pair production by the potential, or by the potential gap. And as you see, adding these guys give minus 2.12. Yeah? Oops. Yeah? Adding the second coordinates give 0.557, and that's minus 0.557. And the boundary condition ensures charge conservation across the boundary. And energy conservation is quite clear as well. I won't go into details of that. You can work it out yourself. It's pretty much like what I did with the legacy field. And the other example, eta changing sign, meaning we have an incoming particle here and an incoming wave here. Or rather wave, we are in classic field theory. And they are so finely tuned that there's no reflection on the other side. There's the incoming wave, which is totally annihilated by the incoming wave, and what is not annihilated is reflected. The conclusion to it all is that we do have, with these definitions, a consistent, workable theory. How to make a many-particle theory, that's another question, which I shall not at all comment upon in this series. I have another point I would like to show you. What do you think about Feynman's adage now? When people say it, it might appear more to be a parrot call or parrot cry. Because the inconsistencies here are unacceptable and no remedy in sight. You might consider that what I have presented here to you is a remedy. There may be others, and maybe you'd prefer some of the others, but this is at least one. Thank you.